Felicia Fuller, and I am the Director of Operations here at GBRI. And today's webinar is being brought to you in partnership with the Collaborative for High Performance Schools. And while we wait for everyone to join us, let me go ahead and just introduce you to GBRI. We are a privately owned online gamified education platform with a mission to make sustainability resources affordable and accessible to everyone around the world. We are located in New York City, and we have a presence around the world. And we are a USGBC education partner, AIA provider, and also education partners with other organizations such as the UN SDGs, CHPS, and the Rhode Island Energy Efficiency Council. We believe a truly sustainable future must also be an equitable one where every human is treated equally and fairly. Our mission is to make sustainability, health, and wellness education available and affordable to everyone around the world. With hundreds of sustainability courses surrounding the topics of energy, water, LEED, net zero, green schools, energy modeling, BIM, and daylighting, just to name a few, Learning Hub at GBRI is your one-stop shop for all your sustainability education needs. And we have a few new releases and upcoming events that I would like to bring up here. So we are very excited to be launching our updated WELL version 2 exam prep and mock exams, as well as a free upcoming session that we have on planning, scheduling, and sustainability, getting started and landing opportunities. So for those of you who are interested, we will share the links for those in the chat later on. And today's session has been approved for 1 HSW LU through AIA. And if you wish to use this course for your LEED or WELL CE, we will provide the details needed to self-report those credits at the end of today's session. And then for those needing them, we will also be issuing certificates of completion within 24 hours of today's webinar. Later, also towards the end of today's webinar, we are going to have a short 7-question poll just asking about your experience today and interest for future webinars. So if you would share your feedback with us, that would be very valuable for us. With that, I would like to now hand things over to Craig Schiller, who is the Executive Director at CHPS. Welcome, Craig.
Thank you, Felicia. Yeah, I'm just going to do a quick overview before we get into the main part of this presentation. As Felicia mentioned, I'm Craig Schiller. I'm the Executive Director at the Collaborative for High Performance Schools, colloquially known as CHPS. I'm really excited today to continue this webinar series focused on schools with GBRI. And thank you, GBRI and Felicia, for that. I'm also really excited for this topic because it is a very important one. Passive House in schools, how we can have performance-based design standards influence our schools and our building environment for the betterment. It's very rare that we have 2 subject matter experts who also work in the industry for a large company that can help influence that industry. So I'm very excited today to have Mike Woolsey and Mir Ali present today from Swegon. Again, we rely on products in our buildings. We rely on their research and their advocacy to make sure that they're doing the right thing. So connecting product manufacturer with CHPS and Passive House is a win-win-win. Go to the next slide. Felicia, I don't think, oh, there we go, great. Before we go any further, this is, I think, the 7th or 8th in a webinar series that, and we have a few more that CHPS has been doing on school science and school buildings. This is possible with our partners, so I have to acknowledge and thank them. Perkins Eastman, Tarkett, Healthy Schools Network, Group 14, IN2 Architecture. These have all been sponsors of this program, as also contributors to CHPS, and I'll mention why that's important and briefly. But again, big thank you for them. Also, Mir and Mike, for your time today. This is also what CHPS is all about, is getting professionals to speak on behalf of our schools. Before we go into what CHPS is in more detail, just a few housekeeping things for this webinar. We are being recorded. This will be available online. We'll have a lot of views after this, so we want to make sure we have a good presentation, and then we'll answer a Q&A afterwards. When you have questions, please put them in the Q&A part of the webinar. I'll be fielding those at the end of this webinar and giving them to our presenters. If you do have comments, we've seen a lot of hellos from all over the world, which is great. If you have comments, put those in the chat box. Please keep muted, just to keep the presentation going smoothly. Again, because everything is recorded, you will see all of this and have all the slides afterwards. Yeah, on to CHPS. So really quick overview, the Collaborative for High Performance Schools is a nonprofit focused on bettering our built environment. We believe every school every student deserves the best place to learn. How we do that is we are a collaborative of architects, school districts, planners, building scientists, teachers, health professionals, and advocates. We are a conglomerate of all of those voices to make best practices in the school environment. We provide technical resources in the form of criteria, building standards similar to LEED, to Green Globes, and to WELL, specific for schools. So again, we crowdsource best practices, we put them into criteria and provide technical resources so that school districts can implement them. The last thing that we do, which is really important, is we do verify schools to help ensure that they meet their intention and their intent. Can't tell you how important that part is. We can all have best practices and the desire for good building, but that does need to be followed up to verify. School districts in particular rely on us to verify their schools to make sure that their design teams meet that standard. We are a membership-based organization, so we do rely on members to not only make our criteria and our technical resources, but also to provide great educational content like this, and really to field questions that we get from school districts all the time. So if you're interested in participating in that, please consider joining us. Right. To date, we've verified over 700 schools across the country. This is actually our 20th year anniversary. We have several editions of our criteria all over the country, including a California-specific version, of Virginia, Washington, Northeast-specific versions. We also have a national version for any school anywhere. Yeah, we can just, for time's sake, let's just keep going. Great. What is school building science? This is best practices in the built environment paired with best practices for how we engage students, their well-being, their professional development, their productivity, and their health. Same thing with teachers and staff. Finally, building science pairs that with the need for school districts, which is to have an operable and low operating cost building. So school building science combines all those disciplines into one. And our webinar series is dedicated for that. So similarly and relatedly, the learning objectives for this webinar is to understand what CHPS is about and what schools specifically are about, and Passive House. We're going to have Mia and Mike talk about Passive House buildings, what their core characteristics are, and in particular focusing on indoor air quality research and how that applies to both Passive House and CHPS. And I believe they're going to be sharing a few case studies and lessons learned along the way. So with that, I will hand it over to our two presenters today.
Thank you, Craig.
Mm-hmm.
Okay. Trusting you can see my slides all right now?
Yep.
Okay. So thank you again to Craig and everyone at CHPS for inviting us to present today. Just to give you a little context about who you're hearing from, we'll talk about our company first and briefly. We are a company that indeed manufactures ventilation equipment, in fact, HVAC equipment of all sorts. But what we view ourselves as doing in the world is helping buildings get built better or renovated better, and with specific attention to the energy consumed by buildings and indoor environmental quality generally. And we can say that you can improve ventilation in the classroom, and you're doing much more than just making the air better. So there's some research that we've tracked from Europe. I should mention that Swegon is based in Sweden with about 17 factories around the world, and we draw on research from all over the place, as you can see here. And I found some data that was interesting. It comes from a white paper that we've published, which will be part of the packet you get at the end of the presentation. But you can see some interesting numbers here that by simply adding mechanical ventilation, you can improve the performance of pupils in schools. And there's lots and lots of research out there about that. And a lot of that is already referenced to CHPS. But also, it seems like the most energy efficient way to ventilate a building would be to just throw open the windows. But in reality, that's pretty wasteful because heat that is already in the building will just go right out the window. So today, it's probably more efficient if you're going to maintain standards to actually use HVAC. And we know a lot of schools still don't have good HVAC, if any. We also know that there's all sorts of correlations between absenteeism in schools, not just in schools though, that as CO2 goes up, all sorts of bad things happen, including attendance rates start to drop. So that's a little bit of background about our view. We also know that just a properly designed ventilation system in general will include means to dehumidify, and that has value for any building, especially schools though. Mold growth and damage from condensation can be addressed, probably eliminated with a good HVAC system. And also humidification. We actually end up at times of the year needing to do both in lots of schools. So a properly ventilated school will also provide humidification, which helps us all stay healthy. So the sorts of equipment that we get involved with are shown here very briefly: air handlers, terminal devices like grills, registers, diffusers, and control products as well for demand control ventilation. We get into a lot more than that, but that's a good overview. As we start to talk about passive house, I can say that passive house in North America has largely been about multifamily residential. But if you look around the world, you'll see that that is kind of an isolated case, because around the world, we're seeing passive house go into all sorts of projects, including schools, which is what we're here to talk about today. So I'll start the course now. My name is Mike Woolsey, Business Development Manager for Swegon. I'm coming to you today from Minneapolis, and I'm joined by Mir Ali. And you've already seen the objectives. So at this point, I'll turn it over for the first segment.
Thanks, Mike. Thanks to Chips and everyone joining here for the time. My name is Mir Mohsen Ali. You can call me Ali. People usually go by Ali. I work with Swegon in the noise control department. And as Mike said, I'm here to discuss chips and passive house and their common goals. Next slide, Mike. Thanks. So, how are we doing with indoor environmental quality, especially in schools? So as per United States Environmental Protection Agency, they say 90% of the time people spend indoors. So meaning we are spending a lot of time indoors and using a lot of energy. So in a way, if we know how to conserve energy within indoors, everyone can contribute, help save the planet and reduce the carbon footprint. Especially these days, building owners spend a lot of time having a complex building systems, trying to build complex buildings, but even after that, they spend a lot of money and they don't get the performance they expect. So we have complex building systems, but we don't get the performance we are expecting. 2004 study done on 224 buildings across 21 United States shows us that including new and existing buildings have identified 3,500 deficiencies, which is a lot. And guess what? Out of those 3,500, a lot of deficiencies were related to HVAC systems, and which causes the most of the problem, and those are within the air distribution system, which is why we are here discussing the chips and passive house at the same time. If we are conserving energy, I guess we could help save, as I said, carbon footprint. Also, through this study, approximately we found that 7,000 large energy-related deficiencies were identified across these 224 school buildings. And a survey done indicate that comfort problems are also a common issue in many US buildings. A recent study done by Occupational Safety and Health Administration, which is in short we call as OSHA, report that 20 to 30% of commercial buildings suffer from indoor air quality problems. this connects back to the point Mike just mentioned. Bad air quality increases the absenteeism within the schools. So if we have a better air quality within the schools, we might have healthy students and a comfort level as well. Also, the survey done by OSHA on a 350 buildings shows that with deficient indoor air quality, found that more than half of the complaints stemmed from HVAC, which is heating, ventilation, and air conditioning systems that are not operating properly. So with this study and done by these 224 building and OSHA as well, we can say that there's a huge demand of indoor environmental quality. So if we try fix those HVAC problems, I guess we are not only contributing having a better indoor environmental quality, but also help reduce the greenhouse gases. Next slide, Mike. So this is a recent pictures we got from a school in US. So if the school management has called us basically to replace the HVAC equipment, saying these are not working anymore, and they want to replace it. Now, in a typical situation, a contractor would come in or a company would come and do the bidding and replace this equipment based on whatever specifications they have. So our retrofit project would just, being said, a retrofit project would replace the equipments, but does it solve the problem? It doesn't. I mean, we are not solving the energy problem here. We are just replacing the equipment, and again, down the line, it could go bad or over the years. So in a typical US schools, the schools are typically 44 years old, and it's been like 12 years since there's any major renovation done. And guess what? The equipment just have a lifespan of 30 years. So if you're doing any retrofit investment, if the school is investing on a retrofit project, it's not worthwhile if they're not considering improving ventilation to help perform students better and the teachers better. So if they are considering these things in picture to have a better indoor air quality and conserve energy, they are also contributing a lot to the planet. Next slide, Mike. Thanks. Also, we have found that in offices there are more people than in any other spaces, approximately 4 times more in office spaces. And to our surprise, classrooms only occupied at 31% of the time. So within a school, the classrooms are only occupied 31% of the time. So this is a red flag. Here we can, with this point, we can say that if a classroom is only occupied 31% of the time, we can cut the air supply to that specific classroom, which is not occupied, and save energy. Either cut the air supply or reduce the air supply, with which we can save a lot of energy. And based on the energy government, they said almost 100,000 public K-12 schools represent 5% of the commercial building energy consumption, which is almost 8 billion in utility bills, and serve 50 million students plus 3 million teachers. So the topic we are talking here today about schools, it's something big. So if we help reduce these bills, $8 billion in utility bills, it's a lot of money, and also a lot of a population here, which is 50 million students and 3 million teachers. So from this graph, you can see that, as I mentioned in my previous slide, this classroom only represents 31% of the occupancy rate. And when they are used, they are full. So they need the air supply, a good amount of air supply. And the best way we can save energy is by having demand control ventilation to the classrooms and other spaces. When we don't have occupancy rate in this classroom or have no occupancy in that, we can cut the airflow or we can reduce the airflow and save energy. Coming to the new schools, new projects in USA, they are larger than existing schools. So the 8 million in utility bills I just mentioned, gonna be increased sooner or later, because the new schools which we are building here are way larger than the existing ones. And guess what? They don't have any fine footprint on how they are going to build energy efficient building, except a few standards to follow. And there are 60 to 100 plus schools for K to 12 grade projects in design phase. So if we get to these schools, or if we involve these schools to help them build better schools which can save energy and at the same time help conserve energy as well, that would be a great idea, which is why we have CHPS here. So why or how can passive house is important, and how it can help CHPS intent, and how they can help the planet save energy. So basically, a passive house focuses more on energy efficiency, whereas CHPS goal is to have well-designed, operated, and maintained schools that can enhance indoor environmental quality. And how they are planning to do it by conserving water, energy, and other resources, so that they can minimize the greenhouse gas. So CHPS is basically focusing on schools, whereas passive house is a broader thing which focuses not only on schools but on every buildings, as Mike mentioned. And sorry, Mike, thanks. And passive house is only focusing on energy efficiency, as I mentioned, and to have more comfortable at the same time. And if by saying that, when we are trying to go with building standard that passive house has designed, it doesn't mean that we are spending more money. We are trying to make these things affordable at the same time, having the comfort level. So what does we get by following passive house? CHPS give us a broader idea, but passive house gives us the footprint on how to conserve energy and be energy efficient, build energy efficient buildings or schools. And CHPS usually, I would say, are in a nutshell, a school that is recognized as CHPS verified is healthier, more environmental friendly, and efficient and cost saving. Next slide, Mike. So how CHPS is doing, I guess Craig already discussed on this, but I would like to mention a few points on how they're doing here. So they have already completed 700 schools across US, and another approximately 300 schools are underway seeking CHPS recognition. 60 school districts have already committed to build new schools to CHPS performance, and 12 states have state or region specific high performance school building criteria, including California, Washington, New York, and many more. Participating districts include Los Angeles Unified School District. To my attendees here, I would just like to point out that LA Unified School District is the second largest school district in the country, whole United States, and they have committed to build new schools or modernize the CHPS high performance building. So a point here to all those engineers or architects, if these kind of big organizations coming forward down the line, they would be requesting buildings or the engineers to have these kind of certifications, which is why Swegon is up ahead and trying to have all this information so that they can have these certifications in place and help contractors, engineers, and builders to help get these certifications. Next slide, Mike. So this is a criteria framework from CHPS. So if you are trying to build a school which is CHPS certified, you can see from this table, they have assigned almost 250 points based on each prerequisites. We have energy, we have water, site, and out of all these, the most point, I would say 33% or 82 points are allocated for indoor environmental quality. And which is why we are talking about passive house and how they can help you get these 82 points or 33% of the points. And if you see this second table, it's kind of tiny, but in the second table, you can see up to 10 points can be achieved for enhanced acoustical performance. So if a school or a space within the school has enhanced acoustical performance, then they would get additional points for that. And companies are, I mean, there are people who do these analysis and tell you how enhanced acoustical performance you have within the building or within the given space. I would touch base on this point in my next few slides. So what are the standards or existing standards we have on energy conservation, or how to build buildings or schools to save energy? So we have ASHRAE 90.1, which is a standard for energy standards for buildings. They do have things in point there to say how you can save energy, but those are for regular buildings. They talk about schools, but it's a bare minimum requirement for schools, and it's talk a very tiny bit for schools. And in the second picture, if you see, there is a guideline on how you can build schools by using these things, but most of the times it has been overlooked. And the second here in my slide here, it says LEED and CHPS. So if you follow LEED and CHPS, they mostly say to go to ASHRAE 90.1 and follow ASHRAE 90.1, which is why we have passive house here. Passive house drills down a bit more on how to build energy efficient buildings, energy efficient schools, which can help save you energy and have better indoor environmental quality at the same time, while not spending much more than you are already. Thanks. So this is a slide which shows you different noise sources. Most of the times, the building owners or the architects or many people doesn't know where the noise is coming from, which is why I have mentioned that part 2 in my previous slides, that 10 points are for acoustical performance. So if you see on the top left there, we got a cooling tower, we got some stack, and then we have some, I can barely see, yeah, but we have some HVAC units, rooftop units, Mike is pointing on, and then we have some exhaust fans on to the right. And just below that, we got a generator. So these things, when they run, they push a lot of air, which makes a lot of noises. And it could be just not within the building, but to your neighbors as well. And most of the cities has bylaws for noise reduction within your limits or within your municipality levels. So if these things can be considered while designing a project, then we could have almost 80% of the 82 points mentioned by CHPS, and also have a better acoustically rooms and classes, so that student can focus on what they're doing. And if you see in the first picture, just underneath it, they have some custom silences there, which can help you where we have a less space or we have space constraint. And these things also need to be taken care as to if we are considering pressure drop, a system effect, and all those stuffs. A lot of time we neglect pressure drop with system effect, and we mostly go with catalog pressure drops, because once it's installed, we might get a higher pressure drop issues, and then the unit might not perform well, and then again we might end up having a lot of energy consumption by the unit. So this is one of the RTU solutions which people usually, or the engineers usually miss. So a lot of times when we have RTUs, especially above the classrooms are above the occupied space. When the RTU runs, it makes a loud noise, and which could transmit underneath the space and have a lot of noise issues. And we have, from our experience, we have seen similar issues in the past. And we would recommend, these things are recommended while considering selecting a rooftop unit to have noise control curb, which can omit noise underneath the roof. Within the occupied space, which can have a noise control. Within a noise control curb, you would have a silencer and panels where the noise could suppress, and you would avoid getting duct bond breakout and transmission loss. So from these things, if we see a lot of issues within the indoor environmental quality and the study I just shared. So if we try conserve these things, or if we try help schools to get better HVAC equipments, to get better things here, and then we would help them conserve energy at the same time, and have probably cut some utility bills on their sites, which would not just help themselves but the whole planet by reducing the greenhouse effect. From here, Mike would take over. Thank you.
Thank you, Ali.
Thanks.
It's interesting to see how the topic of indoor environmental quality has changed in my career. My career started, we didn't even talk about indoor air quality. We didn't talk about energy savings either. It was build buildings, build them fast, go to the next one. But I'm happy to see that it's changed, and it's helpful information that you've given Ali on some tips on how we can build energy efficiently with indoor environmental quality. And that does lead right into Passive House, because Passive House has been on that trajectory for decades now. So over 100, in fact, a couple hundred schools around the world have been built to the Passive House standard already. And that's what we're going to talk about now. And our goal really is to address some of the things that Ali just mentioned. Some of it kind of paints a bleak picture. We've got a lot of work to do. But on the other hand, I think that the Passive House concept is worth considering, because if you follow the recipe, if you will, of Passive House, or the concept, you will address many, many different of the CHPS criteria as well. And that's what we're going to talk about here for the next few minutes. So the project structure, first of all, is different. If you're going to undertake a Passive House project, there's going to be a new participant called the Passive House consultant. That Passive House consultant is going to help guide the project towards certification. And certification of Passive House isn't platinum, gold, silver ranked. It's purely pass fail. You either achieve it or you don't. I find that concept really appealing. And the way you get there, for either new construction, there's a separate program for retrofit that I'll talk about a little bit. You're going to work with a Passive House consultant who actually has some veto power. That Passive House consultant has to stamp the submittals for approval. And we have already seen it on projects around North America, where the engineer signed off on the submittals, the architect signed off on the submittals, and the Passive House consultant says, you totally missed. This is supposed to be about energy savings. I'm rejecting this until you solve this one problem. So that's a new element, and it's a quality control element, I describe it as. Also, during the build of a Passive House project, there's going to be a certified Passive House tradesperson. That person is skilled in the special construction techniques that it sounds kind of scary. That what do you mean special? Well, what's special is that it's new. Things like taping windows and properly installing insulation to meet the Passive House intent is what that's all about. There's 2 air tightness tests. Not only do you have to specify it, you have to install the air tightness methods, test it. If it passes that first test, you go finish your building. And when the building's finished, you test it again. You have to pass both of those. And the reason I talk about air tightness is because everything has to do with air tightness in my mind. There's a lot of other criteria that we'll talk about, but air tightness really drives it. So here's some of the values that you're seeking to achieve in a Passive House project. Air tightness is, of course, number 1, at least in my book, but it's also at the top of the chart provided by Passive House Institute. 0.6 air changes per hour is the target. That's a pretty low number, but it's very achievable. The Passive House concept's been around since the 90s, probably late 80s actually, and thousands of projects have been built with air tightness values of this measure. I heard this week of an architect that says they get 0.2 air changes all the time. It's not an issue. I'm not saying that every building has that sort of air tightness. It's a goal and you have to achieve it. I won't read the rest of this chart, but I want to focus on this one value here, 4.75. That's the magic number, 4.75 BTUs, thousands of BTUs per square foot per year is the annual heating demand criteria. You have to be below it. If you build yourself a building that's got solar panels and it's got great insulation and it looks nice and it tests out at 6 BTUs per square foot per year, it fails. It's not a passive house. So it's a hard number that you have to achieve. As far as comfort goes, you can't exceed 75 degrees 90 for more than 10% of the year. So 90% of the year, you have to be below 75 degrees. It turns out that passive houses are so well built that overheating is a problem. And that's why that value is checked. And then finally, the energy goals. So 19 kilowatt hours per square foot per year. That's a hard number. You can't come in with a project at 30 and expect to become a passive house. The retrofit program is very similar, and I'm not going to spend too much time on that, but I will say that the values are similar. This is still about 19 thousands of BTUs per square foot per year. I should point out, though, that the method of calculating has more to do with how far away from the target are you. It's a very different program than the new construction program, and it's a phased program where you can work with your budget to first do some insulation, then move towards doing something else. Kind of touching on what Ali said earlier, replacing inefficient equipment inside the building may not solve your energy problem. And Passive House Institute's retrofit program addresses that. So is Passive House working? The answer is yes. There's increasing evidence every year, 40 to 80% less energy consumption than a code-built building is what we're finding. You all, I understand, will have access to this presentation at the end. All of these hyperlinks are live, so you'll be able to go do some more research if you like. So what are the 5 key passive house characteristics? Airtight construction, continuous ventilation with heat recovery. Those two are very closely tied. We'll spend most of our time talking about that. But to round it out, these are no less important. High performance openings, so doors, windows, skylights, things like that. Whole envelope insulation, and minimized thermal bridging. So starting with the insulation and thermal bridging, this diagram on the left, it's actually a photo of a wall sample that an industry colleague of mine let me borrow. And it does a great job of showing us what we mean. You can see some insulation here, and you can see how well applied it is. It goes all the way into the corners, and there really are no gaps. This gap is taken care of by properly cut and applied insulation. What you can't see is that facade clips and things like that, things that would go through the insulation to the structure, are thermally broken so that they don't become a source of heat transfer. And the result is a before and after thermogram here, which on the left shows us before, on the right shows us after. The temperature scale is red and yellow are warmest, and blue and dark blue are coolest. So this building obviously was heating up the skin of the building a lot more than this retrofit project was. And you can see that the windows even are performing better. There's less yellow, and almost all green, so pretty homogeneous. And that plays a role, of course. You can do that on any building, and you can save energy by doing that. But you can't save enough to get to passive house requirements. You'll also need to look at the windows themselves. The windows typically are triple pane. They don't have to be. Often they can be a very good dual pane. They're going to have thermally broken spacers, so you have to watch what kind of spacer goes between the glass. And then the frame itself is normally made out of a non-conducting material to achieve passive house certification. Moving then into airtight construction, I think you can drive around any city and see a building under construction and see how it's being wrapped, like this one here. That's not what we're talking about. When we're talking about airtight construction and passive house, we're talking about this sort of airtight construction. So that same sample wall that I had up earlier, if you look around the corner, you can see the inside. So what we are showing here are furring strips. So there's no drywall yet, so that we can see inside the wall. Behind the furring strips is the airtight barrier. So the airtight barrier is on the inside of the building. Then you see the insulation. Some other airtight features include window gasketing and window gasketing on top of window taping. It's very elaborate, and that's where the passive house tradesperson comes in, teaching people how to apply these principles. I hear stories all the time about how passive house tradespeople go out and train contractors on their first passive house project, and they're skeptical at first, and by the end of the project, usually they respond saying, "I'm going to do this on all my projects. It doesn't cost more. It makes more sense. Just nobody knew to do it." So it's an influence that passive house is having on industry that I like to see. But what does airtight construction do? Well, it reduces infiltration and exfiltration. I'm sure most of you, maybe all of you, like me, have sat next to a window that leaks. And in the wintertime, here in Minneapolis, you don't really want that. And you can also feel a draft through the wall. I have experienced that too. Infiltration is anytime the air is coming into the building in any measure outside of the air conditioning system. Exfiltration is just infiltration going the other direction. So it's uncontrolled. If you add an airtight barrier, you control your infiltration. You reduce your air tightness so that 0.6 air changes is achievable. You're also starting to help other elements of indoor environmental quality by keeping the finest of airborne particles outside, those pesky PM 2.5 particles we read about all the time now. And we also do something to reduce the migration of sound into the building through cracks in the building. So this chart gives you an idea that, and I've seen variations of this chart done by others. If you build a building to standard 90.1 code, you'll probably have this much heating that's required to overcome the cold air that's leaking into the building. In a passive house building, you're only providing this much heating to overcome that residual leakage or infiltration. So passive house largely now is telling people this is your first stage of cooling, is a well-built building. It comes at a price though, this air tightness. So buildings must breathe, just like you and I have to breathe. We need to get rid of that CO2 in our bodies, and buildings need to get rid of that CO2 inside. If you have a leaky building, I call them leaky buildings. Let's say even a building built to code, it has an infiltration level that meets your local code. That is a means of getting rid of CO2, granted, and you actually will calculate that as you're designing a building and use it to offset how much mechanical ventilation you actually need to provide, at least in a multifamily residential sort of project. So we need to have that ventilation system running continuously to make sure that CO2 is being replaced by fresh air. So just a step aside here, what is ventilation and what does a system look like? It's important to consider the system because when I say ventilation, I don't mean an air handler. I don't mean a rooftop unit or a classroom unitary unit. What I mean is a system that involves some means of bringing fresh air in, distributing it through the building in a way that's comfortable, and then exhausting the spent air, that CO2 laden air, back outdoors. In a passive house, we're also trying to do some other tricks that I won't focus too much on here today, but we want to provide that fresh air in a way that uses as little energy as possible. So the typical path of air on a larger project, this could be a school, would be through a supply air ductwork that branches off and then goes into an occupied space. And the air flows to like a corridor or a place that's less critical. without ducting. Anytime you reduce the amount of ducting, you get to save energy because energy by the fans and the air handler is consumed generating pressure that's enough to blow the air downstream. You can also do some post-heating and post-cooling. And you also want to make sure that your ERV, as we call them, this air handling unit with energy recovery, is energy efficient. You can get these in 2 flavors. One that would address heat recovery only. That would be valuable for lots of Europe and also lots of the United States and Canadian West Coast. On the East Coast of the United States, though, from the Mississippi River towards the east, usually you're going to require energy recovery ventilation. The difference being that one handles just heat and the other handles heat and moisture. So what is then a typical ERV doing? I'm using the term ERV because that's passive house lingo. That's what passive house participants likes to call air handlers of all sizes. So what do? They bring in outside air, they filter that air in a MERV 13 filter. That MERV 13 filter is very important. We learned that during COVID. ASHRAE came out and said you should use MERV 13 anywhere if you can. It captures PM 2.5, PM 10, other particles. Really important for the outside air for indoor environmental quality purposes. So we're taking dust and allergens out of the air. Really important for the ongoing performance of your HVAC system, because these little particles can start to collect further downstream in the ventilation system and start to reduce the actual performance, the energy performance. There's a heat exchanger. Sometimes we like to call this the first stage of heating and cooling, but really it's the building, the passive house building, that does that. But before we generate any heating or cooling mechanically, we're going to use a heat exchanger to capture heat that's already been generated. So in the wintertime, like we're showing here, that heat is coming from inside the building. We're going to use high efficiency fans to blow that supply air downstream. This is the fresh air. If you're in the building, you're going to be supplying return air for the other side of this energy recovery ventilator. That air is going to be filtered. That's something that's a little bit, has captured a lot of attention because there is no such thing as a perfectly sealed energy recovery ventilator that doesn't have some cross-contamination. So if you have airborne infectious agents in your return air, they could be recirculated when you thought you were blowing them all outside. That's another good reason to have a MERV 13 filter in the return air. So to complete the trip, we have another fan that blows the air outside, and we have some ratings for very low casing leakage. So what does this look like? If you're in Boston, and I know some of you are, on a design day, it's 13 degrees outside, and an HRV will take waste heat coming out of the building at 70 degrees and heat up the heat exchanger, which heats up the outside air all the way up to 62 degrees. That's already a pretty comfortable level that might be warm enough, depending on how occupied the building is. If it's not, then we simply add some post-heating and post-cooling. Similarly, we see that we can also control humidity with an ERV by taking moisture, leaving the building, returning it to the supply airstream. And then finally, and quickly, don't overlook that energy recovery works pretty well in the summer months too, because it rejects heat and moisture from outdoors so that you never have to deal with it downstream. So in this case, when it's 91 degrees out, 43% relative humidity, the air is cooled all the way down to 77, and the moisture level is just about neutral for these conditions. If you're designing a passive house, you're going to have to do an energy model in either CHPS, if you're going to be certified by Passive House Institute, or by Woolsey, which would be used if you're certifying a FIAS certified project. On the certificate that manufacturers can get for their Passive House certified ERVs or HRVs, you see this statement here, which calls out the requirements. So just like buildings are pass-fail, Passive House certified HRVs are pass-fail. To pass, you have to have at least 75% heat recovery efficiency and no more than 0.45 watt hours per cubic meter. So if you speak in inch-pound units, that works out to 0.765 watts per CFM. And what difference does it make is a good question to ask. What happens is there are a couple of ways that you can size equipment for a building, whether it's new or renovated. You can use the time-tested, give me the smallest thing that'll work, because first cost is all that matters. But when you do that, you've given up performance. So here's an example. This was for a school project in New York. We were asked, what is the difference between a passive house ERV and an ERV selected to meet code? The difference is the size. In passive house, we routinely pick a larger size that meets that 0.765 watt per CFM requirement. So by increasing the size of the unit, yes, you add some cost, but you also dramatically reduce the life cycle cost and you reduce your energy bills from day one. So it becomes a life cycle cost product selection. The end result, I could probably talk all day on this slide, but I won't. The end result is that larger unit saves 10% in energy use every year. And usually an air handler is one of the top energy consumers in any building. So it's worth pursuing that 10%. So wrap it up here with some case studies. I mentioned hundreds of projects around the world, 120 pre-K kindergarten passive house certified schools, 169 secondary schools, and several residence halls. All of these are linked, so when you open up your presentation, you can follow any of them to the details of the project. It'll tell you how they're built, how they're, what their energy performance is, and also who the architect was. All sorts of good information is linked from those. One example would be this Riedberg Passive House School in Frankfurt, Germany. You can see performing 90% better than 177 similar schools in Germany. So the climate in Germany is, you can't quite match it in North America. It's a little bit drier, but it's similar to, say, New York, or probably a little bit closer to Chicago, or a little south even. But the climate doesn't really matter, is what the story is. And you can read all about that at Passipedia too. This is that same school. The case study that I read, I didn't participate in this project, but I read about it at Passive House. This is the same project before and after. It doesn't really look like it. You can't really compare it side by side. But the point is that there was dramatic improvement in the way heat transfers out of the building in the wintertime. It really doesn't. So here's another list of schools. We're going to skip those and jump to this one that is now occupied. It is an operating school in Queens, New York. It's called Mosaic Pre-K. It's built, interestingly, within a passive house multifamily residential project. And you can see some photos here. What I want to show you, though, here's a floor plan. It's a smaller project, only 4,700 square feet, built within a 40,000 square foot senior home, and it's certified by Passive House Institute as classic. So what that means is the criteria was 15 kilowatt hours per square meter per annum, or every year, and this building is achieving 13. So another case where Passive House worked. So this is the first project in North America really to get PHI certification. And my experience is that things like this, when they're new, we always start small, then they start to get bigger and bigger. Well, this project was no exception. More on that in a minute. If you go to the roof of this building, the air handler for the school is way up on the roof. They probably could have saved some duct run and some duct pressure loss by moving this unit indoors, but space is a premium in New York. Most everything goes on the roof. So you can see some pretty impressive numbers here. 86% efficiency heat recovery, operating at 0.72 watts per CFM. I could probably spend an hour on this slide. The Passive House consultant on this project offered some advice when he heard what I was doing today. And so he provided all sorts of good advice on things to do if you're going to design a Passive House school based on his experience. And it's broken down by schematic design stage all the way through to commissioning. Mainly, what he's saying is don't count on a super efficient piece of equipment to solve your problems. This all has to work together. And that's what the Passive House concept is all about. So then to wrap it up, because I know there's other things to talk about today, here we are. That first project in New York blossomed. Now there is this project being built. It's called 100 Flatbush. It's in Brooklyn, 146,000 square feet. It's under construction now. It also intends Passive House certification, and coincidentally will be Brooklyn's first all-electric skyscraper. So there are these 9 recommendations that will be part of your follow-up kit. Things that you should think about when you're designing a Passive House school. But we're not going to go through those today. And that is what I had for you all today. So I appreciate your time and the opportunity to talk about Passive House a little bit.
Great. Thank you, Mike and Ali. We have a few minutes left. I've been trying to field some questions as you guys have been going. They've been coming a lot. I'm hoping to get through a few more with the two of you. We may take a few more minutes than this webinar allows. So let's just get going. Okay, we'll try to answer these quickly. Okay, Mike, you mentioned energy modeling. We've got a question from James Carr. Just to clarify, for Passive House, is it modeled energy, or is there a real-time post-construction measurement that needs to be done?
There is both. You model the energy to make sure that your design can be pre-certified, and then the quality analysis or quality control check at the end tests for the energy use.
Great, thank you. A couple of questions on passive ventilation. I've answered a few. I'm going to put a big caveat before I ask this. The biggest challenge we have for schools and students is air quality. Right now, in a recent report from the World Health Organization, 99% of everyone on Earth lives in an environment of poor air quality. Smoke, particulate, pollen, ozone, NOx, nitrous oxide, etc. Our outside air is often not the best, particularly in urban environments. That's the downside of passive ventilation. So Mike, question for you, with Passive House and with schools, how do you balance outside fresh air on those rare, beautiful days and the tight building envelope and the air quality that are so important?
It's mainly about filtration. And we've, like I said during my presentation, that we've learned lots about filtration and how important it is. If you do indeed have outside air conditions that are poor, then that has to be considered during the design process. And if you're in New York, like Manhattan, you're going to change your filters frequently, but those filters actually still work. You just have to change them more frequently than you would if you're building a project in suburban Minneapolis.
What about operable windows, though? I mean, they should all be operable under certain conditions.
Operable windows can do a lot to save energy for conditioning, but they can do nothing to help you filter that outside air.
Yeah. Yeah, great. I worked on one commercial project in which we had literally a light sensor near the window that was linked to outdoor air quality data. So it basically gave you a green light when it was good to open.
Yeah.
That's often too expensive out of scope, but that's the kind of level that's necessary. All right, great. I had a question on the climate zone. I know Passive House, the big thing is high insulation values, very tight building. So can you tell us quickly about how that relates to different climate zones, Florida versus Minnesota?
The efficiency, I guess the question is based on insulation values, correct?
What is the consideration of climate related to Passive House?
Yeah, so it comes down to having the most impact on the insulation values because the air tightness is most important. An energy recovery ventilator has the same performance in Florida as it does in, say, Saskatoon, where it's super cold. It's still super efficient. It just matters less in Florida because in Florida, you have less heating to worry about. On the other hand, you save extra energy in Florida because you're pre-cooling, you're rejecting heat and moisture. So the climate-specific insulation is really important. You'll find that you might actually be able to build a less expensive Passive House the further south you go and benefit more from that than you do from the super efficient HVAC system.
Okay, great. Got a question from Eric about the window to wall ratio. Sorry, I missed this on the presentation. Is it limited to 25% or is that a guideline?
I think that was actually a slide that I skimmed through. It's I think standard 90.1 actually has a ratio. And I don't think Passive House actually has a ratio. It does have a geometry ratio. So surface area to volume. Windows there are some target numbers. I don't have them handy though.
Yep, no worries. Another question, actually, this was an interesting one from Alex. Mirrors on the premise to make lighting more efficient or daylighting. Is that something that you've seen done? I don't think it is in any standard.
Not sure about that. We haven't seen.
I think you'll find that mentioned in the Well certified. Well V2 talks a lot about lighting, and it's like I mentioned earlier. 30 years ago, nobody cared about any of this, and now sound is part of indoor environmental quality, and so is lighting.
And just to bring that back to schools, sound and lighting are two of the most important things, along with indoor air quality, for students' attention and performance. Alex, it's a great question on mirrors. I think this is a great time where designers are doing some really creative things to get to these end goals around natural lighting and acoustics, although mirrors will have a negative acoustics quality. Couple more. We got a question from Judith. Okay, what insulation should be used? Judith, just real quickly, there's two answers to that. One is on the climate zone and the type of the level of insulation. When we get to types of insulation, there's an abundance, and it's a little out of scope, but particularly for residential. Let me ask you this, Mike or Ali, do you have a preference, or do you have a recommendation or type of insulation that you've seen work best?
Mineral wool is an interesting option. The reason for mineral wool, we actually use mineral wool in our product because it has really good sound deadening qualities. It doesn't like to hold moisture. Moisture likes to drip out of it, and it's a really good insulator from a fairly inert material. It's made out of rocks, basically. There's some question about the content of the things that hold the wool together and how it's stuck to whatever it's stuck to. So if you're interested in things like materials transparency, you might want to drill into that a little bit further.
Okay, that's great, Mike. That's actually great. And that was specifically for Florida. So excellent. Yeah. Okay, another question. This is from James. Again, the ERV by Panasonic for residential dramatically reduces the amount of fresh air versus recirculating air in cold weather. How do you account for this when there are minimum fresh air requirements as in a school?
I would say that the benefit of an HRV or ERV in any climate is that it's continuously running, unless you've chosen to turn it off because the windows are open. That's always an option. But if it's running, it's bringing in minimum outside air and it's tempering it before it goes into the space. So if it gets really cold, then you would want to add some air to the air, add some heat to the air coming through the HRV. I'm not sure that got the question, but that's what I'm thinking.
Don't know either. We have a question. This comes up often: lead versus passive house, or in this case, lead versus well versus chips versus GBRI versus green globes. Give us the quick overview on how passive house is different with all these other standards. I know you started with it, but let's recap.
Sure, I'll try to. I've spent a lot of time studying that recently, actually. I guess I would summarize it by saying that passive house is unique in that you pass or you fail. You either achieve the objective completely or you don't meet it at all. And I'm involved with some projects that it's been going back and forth for over a year because of one issue. You would think somebody would just give up and say, close enough, we'll give it to you. That just doesn't happen. Regrettably, I know some of the highest certified buildings in the world have the lowest energy performance. So one of the things that makes passive house so useful is that I showed the numbers that they are routinely very high energy performers.
Yeah, I think that we get this question a lot too. And if you are a passive house building, there's a chance that you could, if you meet passive house, that you could already be LEED or already be CHPS. But CHPS is a little bit different because we have other indoor air quality metrics we weigh on, as well as site things. But can you mention that, like, if you get this acronym soup, and a lot of buildings don't just have one now, they have 2 or 3 or 4 of these plaques in the building.
Right. I think that's an important point. So if you're going to use passive house and you're trying to build a CHPS project, you'll probably build your building to be super energy efficient. You'll probably blow away the CHPS criteria on energy and also solve a lot of other issues in a way that's fairly routine to a growing part of the market.
Yeah, agreed. Starting a lot of thank yous. We got a lot of thank yous for both of you. Irene, who's on our board, Mike gives you her best. Great presentation. Let me see. I want to make sure I get everybody's questions answered. Do I have one? Any experience with preheating air with a greenhouse gas, with like a greenhouse, like a passive solar attachment to preheat air?
I can't say that I have any experience directly with that, but I'm familiar with concepts of, there's all sorts of ways you can preheat or pre-cool outside air. One concept that really never got traction was to bring your outside air in through a tunnel so that it would cool off. So heating it would be kind of like, I guess you could call it a greenhouse source heat pump would be interesting. And I'd say, why not? It definitely would be worth pursuing. I just can't say that I have any experience with it.
Okay. Likewise. I think we've gotten, let me just double check. Is there another question left? I do have one. This is a personal question that we've gotten from schools for both of you. So I hope it's relevant to everyone else. Plenum versus ducted returns. The pros and cons of each. Do you recommend one over the other?
I recommend ducted returns. And that for the reason for that is if you have a plenum return, you're drawing air from a plenum in an uncontrolled fashion. You can't say, I only want the air that's going to this air handler to come from clean sources. So if you have a classroom next to a cafeteria and a plenum return, you'd have to be pretty elaborate about making a barrier between the cafeteria and the plenum in the cafeteria and the plenum in the classroom to make sure you're not drawing the wrong sorts of things to the air handler or the energy recovery ventilator. Far easier and far more predictable and easier to design to use a ducted return. To save some energy in the process. Go ahead, Oli.
Sorry, I would like to add a point there. When plenum returns, you might not have a proper acoustical thing, whereas ducted returns would be, you can add a silencer and have better acoustical performance there.
Yeah, agreed with both. Okay, I think we got through all the questions. So lastly, and everyone stuck around for that. That is so rare. Thank you everyone for taking this extra time out of your day and for this great presentation. Mike and Ali, this was really informative, very helpful, and really thank you for your connection to CHPS and all the research you've done on that side. Again, I want to highlight for everyone, we as an organization are reliant on subject matter experts like these two to help inform and influence our guide. So I'm definitely going to go back with our technical team and see where else we can fit in some of these lessons learned and the passive house requirements. Great.
Thank you for the opportunity.
Thank you.
All right. Thank you everyone for attending. Okay.